Hi everyone, I hope this finds you in good health and good spirits. So in today's lesson, we're going to finish transitioning everything that we talked about with regard to the MS-20 into VCV Rack. So by the end of today's lesson, everything that we were doing on the MS-20, you should be able to do in VCV Rack. If there's anything that you feel like we've missed, let me know. So we'll do that today by talking about randomness and sample and hold, and then also touching on some new things, wave shaping and spatial effects. So with regard to randomness, we're going to talk about sample and hold in VCV Rack and some different sources of randomness in different modules. We'll then talk about wave shaping functions like clipping and wave folding, and then we'll look at adding some spatial effects like delay and reverb. So let's start by talking about sample and hold. So just as a quick review, sample and hold modules are modules or circuits or whatever that sample the voltage of a continuously varying signal and hold its value at a constant level for a certain period of time until it's told to take another sample. So we did this on the Korg MS-20 by running pink noise and white noise into the sample and hold, using the momentary switch or the LFO as a clock, as a trigger source to take these samples, and then sending that output to different parts of the synthesizer to add modulation or filter cutoff changes, things like that. So on the Korg MS-20, sample and hold needed to be sent a signal to sample. Something had to be sent into that input. A lot of sample and hold modules assume that you're doing sample and hold because you want some kind of random signal. And so a lot of them have built-in noise generators. They have noise built in. You can still sample other things if you want, but they're going to have a noise generator built in to save you that step of connecting noise to your sample and hold. So let's start by looking at the random module in VCV Rack. So in the fundamental collection here, there is a small module called random, and it's a little scrawny thing, but it actually has a lot of really powerful properties. And just like what I was talking about a second ago, the random module has a built-in noise generator. It's going to generate its own random signal for us to sample, but we can always add additional signals in as an input. So let's just walk through some of the different controls on this module. I'm going to connect its output to our scope here. And we'll zoom out some. And we can take a look at everything in the scope here. So I'm going to start by bringing the shape knob all the way down to 0. We'll talk about why in just a sec. But as we look in the scope, we can see that we're getting these random voltages that are moving in a stepped function, which is what we would expect from a sample and hold. It produces these stepped functions. And this rate knob on the left is going to change the rate at which these samples are taken. If I slide it up, they're going to happen more frequently. And if I slide it down, they're going to happen less frequently. And they can happen very, very slowly. Now, underneath this rate slider, there are two inputs. One of them is not labeled. This module is a little confusing with regard to where the things are labeled. So this first input is a CV input for rate. So it's part of this slider. And this will take a volts per octave input. So depending on which voltage you send it, it will take, its rate will go up or down. And then underneath, where it's labeled trig, this is a trigger input that's going to accept triggers to change the rate. So some sort of external clock source. So let's go ahead and use that instead of this slider. I'm not going to walk through how to use the input knob here. You guys can explore that on your own. But with regard to the trigger, let's use an LFO. We talked last time how a pulse wave LFO can act as a gate or a trigger. So we're going to do that here. I'm going to take a blue cable for trigger. And once I connect that, as I change the frequency on this LFO, our samples will happen more or less frequently. If they're happening very fast, it just looks like a noise signal. And if they happen more slowly, we see that stepped sample and hold pattern. Okay, so now let's talk about the shape slider. So the shape slider is going to adjust the shape of each of these four outputs, different forms of random interpolation. So when it's set all the way to 0, all of these outputs, no matter which one you're using, it's going to look the same. It's going to have this stair-stepped function of this random output. So we can set it to step here. It looks the same. Smooth. Looks the same. Exponential. looks the same. So no matter which output we're doing, when it's all the way down at 0, they're all going to look the same. However, as we move up in the shape slider, these different outputs are going to produce different results. So we're going to start here with the linear output. The linear output is going to interpolate, that is, find some way to connect between each of these random voltages, and the linear output is going to do so linearly with a linear slope. And this kind of works like a slew limiter. It's just going to start adding little linear slides in between each voltage. So you can see that now, like instead of these hard steps, there's a little bit of a slope as I move this up. And the further up I go, the more gradual those connecting lines get. When we go all the way to the top, we just get these smooth connecting lines. So it's taking the entire clock value, the entire amount of time in between each sample to connect one voltage to another. So we just get this gradual connection between them all. If we go down to exponential, it's going to work in a really similar way, except this time it's going to interpolate with an exponential slope. So you can see that if I start to connect here, instead of those straight lines, we now get these kind of arched exponential curves. And the further we go, the more gradual those exponential shifts are going to be, and the more it bends towards being just another linear slope. And by the time we get all the way to the top, it's just linear again. So when they're all the way up, linear and exponential are going to look the same. But in between, linear looks more like a slew limiter, and exponential gives us all these cool exponential curves. It might make sense to go ahead and connect these to an oscillator and hear some of these as we're moving through them. So I'm going to go ahead and take our output here. Let's go back to linear real quick. Connect that up to our volts per octave, and we'll send a sine wave into our mixer. So there's our just stepped function as we gradually increase our linear output. You can see here that connection. Let's do the same thing with exponential. So it sounds similar, it's just with exponential, the bends happen a little faster. So those pitches we're getting are kind of high. So you can see we've got this unipolar bipolar switch. I'm going to go ahead and switch that over. So instead of ranging from 0 to 10 volts, we're going to go -5 to +5. It'll give us some tones that are happening on either side of our frequency knob here. Okay, so let's look at the other two outputs here. The next one, step, is going to interpolate with a series of steps. When we have it all the way down at 0, there's going to be no steps in between each of these voltages. And then as we move up, we're going to start adding a series of steps that connect each of these voltages. At the maximum, we're going to have 16 steps. And depending on how fast your trigger is happening, they're going to be really fast or they can happen more slowly if we slow our LFO down. Speed it back up a little bit. So it's kind of looks like the linear output, except instead of moving in straight lines, we get these little up and down staircases of discrete steps. And then the last one, smooth, it does a kind of a strange interpolation using a sine wave, where it kind of is just going to gliss around through a sine wave. You can see when we go all the way to the top. It's going to connect each step with a sine wave shape. When it lands on the voltage that's sampled, it'll stay put for a while, and then it'll start the next sine wave with the next voltage. So we go from the steps gradually up to the sine wave pattern. So in addition to this polarity switch, which we already talked about, there's this switch that moves between absolute randomness and relative randomness. So absolute randomness is going to be a randomness in which all values are equally likely. So for instance, if I'm at negative 5 volts, I'm just as likely to have positive 5 volts come next as I would say negative 4 volts, negative 3, 0, etc. They're all equally likely. On relative, we get what's called a random walk or sometimes called a drunk walk. And in relative randomness, values that are closer to the previous value are going to be more likely than other values. So for instance, if I'm on negative 5, negative 4 would be more likely to come next than, say, positive 5 because negative 4 is closer to negative 5. So it's going to be privileging values that are close to the current value. And as a result, you're going to get a series of voltages that are still random, but that are a little more connected and that move in a more connected fashion. And this is going to be better if we want to be like improvising these melodies. You can hear how things seem a little more connected and less disjunct. So this is back on absolute. And this is our relative random walk. So the last thing we'll look at is our last little input here. This is the external in. This CV input up here is just a CV input for the shape if you wanted to automate that somehow. But this external in is if we wanted to send some external source in to be sampled and held. So let's do that with another LFO. I'm going to just take a sawtooth out and send that in. Use a green cable, I suppose. And so we'll slow that down a little bit. We'll increase the rate here so that we can see it. And so now our samples are being taken. Doesn't matter which one we're on. We're at the bottom of the shape knob, so it's all going to be just stair steps no matter what. But we can see this sawtooth shape because we're just sampling and holding this sawtooth. Go back to bipolar. Move it a little faster. And maybe I'll do something other than linear. I can do the smooth connection between these voltages. Maybe we'll do a triangle wave instead. So we've taken our smooth triangle wave from the LFO and we get this kind of wobbly one from doing the smooth transition here. We'll do the step one maybe. We'll get even more steps moving through them. So if you want to do some actual sampling and holding of some voltage you're working with, you can just plug it into that external input and that'll take care of that. Okay, so let's build a patch using this random module, see some different ways we can use it. So I'm going to start by pulling up that random module itself. And I'm going to send that into a VCO, just like we did a second ago. So I'll just move that shape all the way down, and we'll take our linear voltage, and we'll use that as our volts per octave input. And let's take our triangle wave out, and we'll listen to that. We'll also send that into our scope so we can see what's happening. Oops, not that. We'll take the voltage here. Now we're getting a lot of really high pitches. It's kind of jumping all over the place. So instead of having a really wide range, I want to narrow that range some. And I'm going to do that by adding a VCA. I'm going to set that right here in front, and we're just going to stop off in this VCA on our way to the oscillator. We'll take the output of the VCA into scope. So right now it's not any different, but as I bring this down, our randomness is going to happen in a much narrower range now. Okay, so this is a little better, but I'm still getting... These pitches are so random, it doesn't actually sound like any kind of melody I would recognize. So now I could add a quantizer, and maybe I can quantize that randomness into some more discrete pitches. So we talked last time, not last time, but we talked last week about the built-in fundamental quantizer, which allows you to choose which pitches you want from these 12 sliders. That's kind of handy. There's also another one by ML Modules that looks kind of the same, except it's got this little keyboard interface, which might be a little easier to read. You don't have to count all the sliders to figure out which one is F sharp, say. But there's still a different one that I want to use, which is this JW quantizer, which has an input and output, but then also lets you choose the tonal center with this knob here and the scale with this knob here. So we're going to come out of our VCA into our quantizer. I want to do the VCA before the quantizer. And right now it's going to take whatever random voltage comes through the VCA, and it's going to quantize that into voltages that are in the C melodic minor scale. Let's choose something else though. Let's do something weird like D sharp pentatonic scale. Okay, so this melody is a little more like, sounds a little more melodic, sounds like something we would actually expect to hear in a piece of music. Let's do a little more though. Let's maybe add an envelope to this. So I'm going to go grab my ADSR. And we need the ADSR to shape a VCA. So we're going to connect these two together. I'm going to take our output here, send it into the control voltage of this VCA. And then we're going to run our melody here through that VCA on its way to the mixer. And now we need something to trigger this envelope generator to start. We could do it with the keyboard, but that might be weird because this thing's going to be changing pitches, and we don't want it to change pitches in the middle of our envelope. So it might make sense to have something that's going to trigger this also trigger this. So let's do that with an LFO. I'm going to take an LFO pulse wave out, use that as the clock for my ADSR. And I'm going to use that same square wave as the trigger for this random generator. So now every time this LFO sends a trigger, sends a gate, it's going to choose a new voltage here, and it's also going to start a new envelope here. And we can have this happen a little more quickly. Maybe change the envelope a little bit, get something a little more plucky. Okay. And so our melody is still kind of high because we're using a unipolar randomness. We could hit to bipolar, and it's going to have a slightly different range. All right, this is sounding good. Let's go ahead and stop that, and we'll come back to this here in a little bit. So now I wanted to talk about a couple other modules quickly that allow us to work with randomness. There's the Audible Instruments Utilities module. We haven't actually looked at any Audible Instruments modules, but these are all really, really great, really sophisticated modules. And this Utilities one is a small, elegant little module with 3 compact sections. There's the signal section, which can invert and rectify signals. This middle logic section, which can merge 2 signals and output the minimum or maximum voltage. Both of these are really handy. I'm going to include a video on Blackboard that'll walk you guys through these by Omri Cohen. I'm not going to go over these sections myself, but I will just quickly point out the bottom sample and hold module. This is going to be a lot more straightforward sample and hold. You don't have all these 4 crazy outputs that do all these different mathematical things. You just have a very simple input, output, and then trigger or clock, which is just like what we had on the MS-20. These 3 jacks, you can send something in to be sampled, send it out, and then send something in to tell it when to take its samples. If you don't send anything in, it's just going to sample white noise, and it's got a built-in noise generator. And since it has a built-in noise generator, they've given you a noise output here. We've got it there, may as well let us use it. So I'll include the Omri Cohen video, which walks through a whole module and also gives you some really great ideas about different ways to use sample and hold in VCV Rack. Another one, which is kind of fun, is the Bog Audio Walk, or Walk 2, I believe it's called. It's a 2-dimensional drunk walk signal generator. It produces 2 random signals with independent controls. So there's an X and a Y. The X is going to produce random voltages that move left and right. The Y is going to produce random voltages that move up and down. And together they have this interface where there's this little worm that's kind of crawling around, and you can see the different places it's going. If we increase the rate, it's going to move, this is the X rate, so this is going to increase the speed at which it moves left and right. We can do the same thing with its up and down movement by increasing the Y rate. It's got an offset, which allows us to move this maybe just into the positive range or just into the negative range, an X offset and a Y offset. And then it also has a scale knob with which we can kind of narrow the scale that it's moving through. And then we've got a CV input for the offset, the scale, the rate, and then an output for the X. So you can see how this is going to end up looking in the voltage world. This is the movement of its X-axis. This is the movement of its Y-axis. You can see they're pretty independent of each other. Then there's also a dist output, which outputs a 3rd signal that's kind of a combination of the 2 using kind of a complex formula, which would end up looking like that. And lastly, there's this jump input, which if you send a trigger into this jump input, or if you just click in the interface, it'll jump to that position, or it'll jump to a randomly new position if you just send a trigger in there. So that's kind of handy where it does these walks where things are relatively connected. You can slow that down, you can see that. But then we can always just click in there and it'll jump to a new position. So this is kind of cool because it generates these 2 different random walks. You could send one to an oscillator and one to a filter and have them be relatively connected but still independent. So that's an interesting one for you guys to explore on your own. All right, so now let's transition and start talking about wave shaping. A wave shaper is any module that changes the shape of a wave. Sounds kind of obvious, but there's all kinds of different wave shapers, some which do relatively simple, straightforward things, others which are really complex. So some wave shapers have just very specific operations. There are some wave shapers that all they do is they take a triangle wave input and they will round it into a sine wave. Other wave shapers will just do clipping. So they might clip a sine wave to create distortion. We kind of talked about this a little bit with the filter last time. We'll go into it in a little more detail today. But most often, wave shapers are going to create more complex waves. They're going to take a relatively simple input, and by changing the shape of the wave, they're going to add lots of harmonics, and we end up with something that's more complex. And this kind of brings us back to that distinction that I talked about the first day we were talking about modular synthesis between East Coast synthesis and West Coast synthesis. East Coast synthesis, which we've been spending most of the semester with, emphasizes subtractive synthesis, where we're starting with really complex waves like sawtooth waves, white noise, square waves, and then we use filters to reduce the amount of harmonics that are present. But very often in West Coast synthesis, we're going to start with simple waves like sine waves or triangle waves, but then we're going to use wave shapers to change the shape of those waves and add harmonics. So rather than starting with something big and then chipping away at it with a filter, we're going to start with something simple and then use wave shapers to add lots of harmonics and make some cool new sounds. So that's another kind of distinction between the East Coast and West Coast styles. You may remember from early in the semester, we talked about the fact that waveforms with sharp corners or jumps, quick jumps like a pulse wave, normally have higher harmonic content. So having these quick jumps, these sharp corners, increases the harmonic presence and makes things brighter and buzzier. And so whenever we clip a signal, we're going to, as we talked about last time, kind of chop off the top or the bottom or both of a sound wave. And that's going to add these sharper corners. And in so doing, we change the shape of the waveform. By adding these sharper corners, we add higher harmonics. Now, most often when we experience clipping, we're not doing so through a wave shape. We're actually doing so by exceeding the volume threshold. So if you're working in a DAW or you're playing sound through a small amplifier or something like that, and maybe you turn the volume up really high. And when you do that, you start to hear some distortion in the signal. You start to hear some crackling or some buzzing. And the reason that's happening is the signal is getting clipped. So if you look there on the slide, you can see at the top there's a graphic showing the original signal. And there's a little sine wave there that has been turned up so that it's exceeding the top and the bottom threshold. So it's too loud for the amplifier or the computer program to keep up with. And so what you end up with is what's shown at the bottom of the slide, is the tops and the bottom of the sine wave there have been clipped off, almost like somebody just took some scissors and just clipped along that dotted line and chopped the tops and the bottoms of those sine waves off, and we end up with something that looks a lot like a pulse wave. And because it has these sharper corners now, it's going to have a lot of higher harmonics, and it's going to be brighter and buzzier. Now that's what happens when we hear distortion when we turn up a guitar amplifier really loud, or when we have too many sounds happening at once in our DAW. And it's also what happens if we want to use a wave shaper to clip a signal. And there's two types of clipping. We mentioned last time that the VCF module does a kind of soft clipping. Hard clipping is what we just described, where the tops and the bottoms get lopped off as if with scissors, creating these pulse wave-esque timbres. Soft clipping, on the other hand, is where the edges are cut off, but the sharp edges are still allowed to be a little bit rounded, and so they're not going to create quite as many higher harmonics as hard clipping. And to show this, let's walk through this with a Bog Audio clipping module, or clipper. So we're going to send a sine wave into our clipper here. It's got 2 inputs and 2 outputs. And we'll send that there. We'll use a digital sine wave, and we're also going to send that into both of them. We're going to send the pure sine wave and then also the output from our clipper into our scope. So right now they're doing the exact same thing. And the clipper here has this adjustable threshold. So once we lower this threshold, we're lowering the point at which things are going to get clipped off. So right now it's at 0 dB, but as we begin to lower it, let's go ahead and send things into our analyzer as well. So right now we've got a sine wave with no overtones. There's this little one that's showing up because the clipper's already doing a tiny bit of work. And as we lower this threshold, we get that, we can see that we're clipping off the top and the bottom of this sine wave, and we're starting to generate some of these higher harmonics. And the more that we clip off, the more pulse wavy that signal gets, the more harmonics we generate. But also you'll notice the more that we clip off, the narrower our wave gets, and so it actually gets softer. So we have this output gain where we can kind of boost things and bring the volume back up. And now it almost looks like we just full-on changed the sine wave into a pulse wave. Now right now we're doing hard clipping. If I were to change this to soft clipping, you can see immediately we've got less harmonic presence in the analyzer, and the scope here shows us that our corners are a little more rounded. They're still pulse wave looking, but they're not sharp corners, they're slightly rounded corners. So that's the clipper module. It's really straightforward. It just does this, performs these 2 different clipping functions. One other thing that I'll point out about it, though, that's kind of cool is if we send 2 different waveforms in to the right and left input, it will mix them together, and we get this kind of combination of our 2 different inputs. It kind of merges them together, and we can get different waveforms by doing that. So now I'm mixing the sine wave and the triangle wave, and we're getting some interesting shapes through the combination of those 2 waves. Okay, so now let's look at a slightly more involved module that does some different wave shaping functions, and that is the volt debriatus. So the debriatus has 4 different wave shaping functions, and we're going to look at each of those real quick. So right now, we're just hearing our sine wave, and let's look at this first wave shaping function. This is wave folding, which is a really common wave shaping function. The way that a wave folder works is that when a signal reaches a certain threshold, which is what we're going to set with this knob, the signal doesn't get clipped off. Instead, it gets folded over. It's going to be told to change directions. So once the sine wave here hits the threshold, it's going to keep finishing its sine wave shape, but it's then going to change direction to do so. So you'll see as I increase the threshold here, we start to get this little rounded shape on the top and the bottom. And basically what happens is the top of our sine wave, instead of just going all the way up and over, it's going up, hitting the threshold. It's being told, okay, change direction. And then when you hit the threshold again, change direction again. And it keeps doing that up and down, up and down. And as we increase or decrease the threshold, we're going to get more and more of these folds. And these folds introduce more and more harmonics. Next is the crush section, which is a bit crusher, which is going to change the sample rate, which results in kind of a broken, stair-steppy looking waveform. It kind of looks like it's been sampled and held, which you can see here. As we increase this, you can start to see the sine wave there. It looks like it's being sampled and held. We get this staircase-like shape. And you can also hear that we're getting some higher harmonic presence. There's some aliasing that's happening. This is what bit crushers do. They introduce this aliasing on purpose. So we're getting this high harmonic fold over. I'm going to skip this distort one for now and jump down to saturate. Saturate does just hard symmetrical clipping. So we do this. This is just like what the clipping module did. The more that we increase this saturate, we're going to get that pulse wavy shape. And then this last one, distort, does a kind of soft clipping, but it's not just regular soft clipping, it's called asymmetrical clipping. And basically what asymmetrical clipping does is we're going to make the signal louder, and the top part of the wave is going to be allowed to just get louder and louder and louder, but the bottom part of the wave is the one that's going to get clipped off. So we get these kind of funky looking waveforms, and it's going to introduce some light clipping. So the top is allowed to get louder, but the bottom part gets clipped off, hence asymmetrical clipping. And of course, you don't have to just use one of these. We can have some kind of combination. And get some really interesting sounds. I remember this starts with a sine wave, so this starts with no overtones, and all these different processes are contributing to this really rich sound. And of course, all of these have their own CV inputs and attenuators, so we could add an LFO and modulate some of these parameters. So now the wave folding is changing at the rate of this LFO. So I'm going to go to that patch that I started a second ago with the random pitch changes, and I'm going to add some wave shaping into that. Okay, so here we are. I'm going to pull this envelope generator aside, and we're going to add the volt debriatus in here. And before we make our way into the amplifier, we're going to stop in here. Let's do a little bit of wave folding maybe. Maybe a little bit of saturation, distortion. And maybe we'll even do a little bit of modulation of one of these parameters. So let's add another LFO. Let's have a slow sawtooth that's gradually changing the wave folding. Maybe we'll use the same triangle wave here to change the amount of distortion. Yeah, that sounds pretty good. The last thing we're going to cover today are some different spatial effects. So you guys are probably familiar with these different spatial effects from other digital audio work that you've done, though we haven't really talked about them in this class at all. So we're going to talk about delay and reverb. So delay is pretty straightforward. Delays create a repetition of a signal. Just they create an echo after some variable amount of time. So when we're working with delay, we can set the delay time, and that'll be the distance between when we hear our original sound, our input, and then the time later that we hear some echo. Now, most delay units, delay modules, delay plugins, whatever we're working with, will have an internal feedback loop. That is, the echo that they create is then fed back into the delay so that we get an echo of our echo, and then we get an echo of our echo's echo, and then we get an echo of our echo's echo, et cetera, et cetera. So up on the slide there, you can see the delay module that's part of the VCV Rack fundamentals, and it's got 4 different parameters there. Time is going to control the time between the input and the repetitions. And then there's a feedback knob that controls the volume of the echo's echo. And by extension, that changes the number of repetitions. So for instance, if our feedback is set to 50%, then our echo is going to be 50% the volume of our input. And then our echo's echo is going to be 50% of that. And then our echo's echo is 50% of that. So our delay signal is going to get softer and softer pretty quick. If we set that to 90%, each echo would be 90% of the original's volume, and so they're going to take a lot longer to fade out, then there's going to be a lot more repetitions. If you set it to 100%, every echo is the same volume as the original, and then your delay would just never end because there wouldn't be any fade out. It would just continue and continue and continue. So let's go ahead and add some delay to the patch that we're working with here. So I'm going to take the output from my VCA here. I'm going to send that into this delay, and then the output I'm going to send up to my mixer. And so I've got 2 channels now. I can listen just to the dry sound and just to the sound coming from my delay module. Let's listen to them both together. I'm going to zero out this feedback at first, and now we're just hearing the original and then 1 echo. I'm going to change the delay time. Delay time is now 1 second. Let's go ahead and slow down our random tones so this is easier to hear. Get rid of our sustain. So we can hear 1 echo for each note. As I increase this feedback, we'll start to hear several repetitions of each note. Maybe we'll make our delay time a little shorter to make that easier to hear. So this is no feedback, and this is with feedback. Increase our release time and give those things a little more body. Okay, this color knob is effectively a low-pass filter that's going to filter the delayed signal. So if it's all the way open, our sound is pretty bright. And if we close it up, our delayed signal gets a little bit rounder. And then lastly, we have a mix knob, which controls the balance between the wet and the dry signal. If it's all the way to the left, we just hear the original, the dry signal. If it's all the way to the right, we just hear the delays. And if it's right in the middle, we hear a healthy balance of both. But since I'm going through my mixer up here, I'm actually going to move this all the way to wet because I'm getting the dry signal right here. So I can just hear the dry here and then the delays here. And I can control the volume of those with this slider. Now, some of you guys might have noticed while I was moving this time knob around, if you change the time while a delay is still moving, very often you'll get these weird tape speed effects, where if you're moving it up, you kind of hear things that are like, sound like they're slowing down, and if you move things to the quicker delay time, things kind of sound like they're speeding up. And you could send a LFO or some other kind of control voltage in there to change that time and get some of those tape speed effect changes, which is kind of cool. All right, so let's mute that. And now we're going to talk about reverb. So reverb is, again, something you guys are probably all familiar with already. Reverb is short for reverberation, and reverb consists of very quick reflections of a sound, usually reflections that are shorter than 50 milliseconds, so our ears can't really distinguish them necessarily as being a repetition of a sound. To us, it just sounds like the sound is sustained or kind of made to last longer. These reflections, which happen really, really quickly, also gradually decay, and they're often going to decay at different speeds at different frequencies. So reverb occurs naturally in a lot of different spaces, and you may find reverb if you walk into one room, say, where the reverb is really low in pitch, where the lower frequencies are going to be reinforced based on whatever the room is made out of or the size of the room or whatever. If you were to clap your hands, the reverb is going to sound kind of low and dark, and other rooms might have very bright reverb where the higher frequencies are the ones that are reinforced and the low frequencies decay rather fast. So if you were to clap your hands in that room, the reverb might be very bright sounding and the higher frequencies are reinforced. Now, reverb is a natural property of a lot of different closed-in spaces, but it can also be reproduced electronically, and there's a few different ways we can do that with analog electronics. Number one is a spring reverb. So in a spring reverb, the audio signal is sent literally through an actual physical spring. And as the audio signal is sent through that spring vibrates and it creates additional waves that move through the spring. And that creates kind of a sense of there being some reverb, some reverberation. Spring reverbs are really common in guitar amps. So if any of you guys are guitar players, you've probably had an amp with a spring reverb built into it. And the effect of a spring reverb, if there's only one spring, it's almost like an effect of a one-dimensional room. Now, most rooms are 3 dimensions, so spring reverb sounds kind of fake. It doesn't actually sound like a reverb that sounds like an actual acoustic space. It sounds cool. It sounds really cool, but it does have an artificiality to it. So sometimes spring reverbs will add several different springs. You'll see spring reverbs with 2 or 3 springs, like the one on the slide. And that kind of adds some dimensionality. Each of those springs will have a different tension, which kind of makes the spring reverb sound a little more authentic, sound a little more like a real room. Then there are plate reverbs. Now in a plate reverb, it works really similarly. The audio signal is sent through a large plate that's suspended from springs, which you can see on the slide there. There's a transducer attached to the middle of that plate, which sends the sound through the plate. And then these additional waves are created as they move through the plate. Now, the difference between a plate reverb and a spring reverb is a spring only has 1 dimension, length, whereas the plate has 2 dimensions, length and width. So plate reverbs sound a little bit more realistic because they sound like a room that has 2 dimensions. Imagine a room that has length and width but no height. So one other difference between spring reverbs and plate reverbs is spring reverbs can be quite small. It doesn't take much to have a spring. A lot of hardware synthesizer modules have actual literal springs built into them. And we already mentioned guitar amps having spring reverbs built into them. Plate reverbs, on the other hand, are quite large. The plate that you see on the slide there is probably the size of a twin bed mattress. So plate reverbs often take up a lot of space. So there are 2 reverb units that we can look at in VCV Rack. One is a relatively simple spring reverb emulator made by Bufaco. The Bufaco spring reverb is a clone of a hardware module that Bufaco makes. Bufaco actually makes hardware modules, and they make a spring reverb that actually has springs built right into it. And we're going to look at the Bufaco reverb module here that emulates their actual spring reverb. We'll send this down here next to our delay. We're going to take the signal from our amplifier. We're going to send that in. You'll notice that the spring reverb has two inputs. Oops, sorry, I put down here. Input 1 and input 2. And each input has its own volume slider. Right now they're both muted, but I'm going to bring up this slider for volume for input 1, and you can see that we're starting to get a little bit of signal, though it's soft. And then it's got a few different outputs down here, actually just two different outputs. One sends a mix of dry signal and wet signal, so let's start with that. I'm going to mute our original and just listen to what's coming from the reverb. So this big knob here, that's kind of the focal point of our attention, is just a dry-wet balance. If it's all the way to the left, we just hear the dry sound. All the way to the right, we just hear the wet sound. And we can add a second input if we wanted to. So I could maybe take my delayed sound as a second input. And then I could control how much of the dry sound and delayed sound I want in my delay, in my reverb that is. And then we're using the mix output right now, but we could also just use the wet output, which is going to ignore this big knob here, and it's just going to send the wet output. So which works for me since I'm using a mixer here. I can have the dry and then the reverb here, and I could bring the reverb down if I wanted to. The last thing I'll point out is there's a high-pass filter here, which will run the input through a high-pass filter if you want to get rid of any low frequencies before you run it into the spring reverb. So that sounds kind of nice. We can maybe add our delay back in. And let's look at one other reverb unit, and that is the Valley Plateau reverb. So the Valley Plateau reverb is a very powerful reverb unit. So whereas the Bufaco Spring reverb is really elegant, it's just got a few simple options, one big knob. It's really easy to use. The Valley reverb, the Valley Plateau reverb is a lot more involved and is a lot more powerful, but it also can be a little bit intimidating. So I'm going to go ahead and pull that up here. As I said, the layout can be kind of intimidating, but there's a few things I'm going to point out just to make it a little easier to manage. First of all, we have these big knobs, and then we have a bunch of little knobs. The big knobs are always the actual parameter of the reverb that you're exploring. And the little knobs, you'll see, every time you see a big knob, you'll see a line coming out of it that moves through a little knob into a CV input. So that tells you that the input jack here is a CV input. These little knobs are attenuverters for whatever the big parameter is controlled by the big knob. So before we're messing with modulating anything and doing any CV inputs, we're just going to ignore all those little knobs for now. And so you can kind of, almost like put blinders on around the outside of that module and just look at the big knobs, which tend to be situated more towards the middle. So we can look, we've got two inputs, a left input and a right input, and two outputs, a left output and a right output. So let's go ahead and take our sound from our amplifier here and send that into our input. And then we'll take the output here and send it up into our mixer. The first parameter we see up here is pre-delay. And what pre-delay is the time between when we hear the dry signal and when we start to hear the reverb. If you've ever been in a really big building, a really big open space, maybe like an airplane hangar or something, you'll notice that there is reverb in those spaces, but it takes so long for the sound to move across the space and like hit one of the walls and bounce back that very often you'll hear some space in between the original sound, whether it's you clapping your hands or shouting or what, and the reverb. And that's what this pre-delay is meant to imitate. Can actually add some space in between the original sound and the reverb. Goes up to 500 milliseconds. I'm going to leave that as pretty short for now. Underneath that, we've got a dry volume and a wet volume, which we could control proportionally. Then you can see the next, we've got these kind of teal or aqua-colored input filter. So this filters the sound before it moves into the reverb. So if you want to filter the dry signal before things are sent into the reverb, you can adjust that. There's a low cut filter and a high cut filter. So these kind of work differently than the low pass, high pass on the MS-20 with regard to how the knob moves. They both go 0 to 10. 10 is where the filter is all the way open, and 0 is where it's all the way closed. So if we wanted to reduce some of the high frequencies in the input before it moves into the filter, we could bring those down. I'm not going to mess with the low because we don't have a ton of low frequencies as it is. Maybe a little bit. Yeah, it doesn't make much difference since our sound is kind of high to start with. I'm going to skip over this middle section, and then you'll notice we've got the same pair of filters down here for the reverb itself. So we can filter the sound going into the reverb, and we can filter the sound coming out of the reverb. So I can get rid of some of the highs on their way out of the reverb. We just end up with kind of a low reverb that has a lot of low presence. I'm going to go ahead and add that back in. Now let's look at what we skipped over here in the middle. Here we've got the size, which controls the size of the room. You see it moves from small to large. Just like the delay time, as we move that, we get some weird tape effects. So this is going to control how many repetitions, how much time between repetitions, etc. And then over here we've got the decay time, which is literally just the speed at which the reverb fades out. It's almost like the release time or the decay time. If this is higher, the reverb is going to take longer to fade out. If it's lower, the reverb will fade out relatively quickly. We've got a diffusion here in the middle. Diffusion is kind of one of those weird reverb parameters. A lot of people don't know what it means when they're working with reverb. So diffusion really has to do with it's kind of an analog to the number of surfaces in a room. So if you're in a room with 4 walls, there are 6 surfaces for the sound to bounce off: the 4 walls, the ceiling, and the floor. But imagine you're in a room that has kind of a weird shape, like maybe an octagon-shaped room or something like that. There's a lot more surfaces, it's a lot more complicated. The sound's going to be bouncing in a lot of different directions, and depending on what the room is made out of, that might cause the reverb to last longer or last less. But it's going to make a more diffused, washy sound. So the higher this diffusion is, the reverb is going to sound washier, it's going to sound more smeared together. If we reduce this diffusion, we're going to end up with a less complex reverb, a less washy reverb. And you can actually hear, if we turn it all the way off, you can actually hear the individual repetitions of the sound, the individual echoes. There's also this button here which diffuses the input. Let's turn that off. Now we can really hear those individual echoes. So it gives it this kind of granular sound, which is kind of neat. I'm going to reset all those as we move on to talk about what's at the bottom here. So the last thing with the big knobs that we see is some modulation, and this is literally a frequency modulation. Now, in the original plate reverbs, sometimes you would get this ringing sound. It was almost like kind of a feedback. And one of the ways that audio engineers found that they could eliminate that ringing sound was by adding a little bit of frequency modulation. And so we've got that down here for that reason. You can use, you'll see 3 controls that are really familiar to us from the MS-20. We've got modulation rate, or speed, frequency of the modulation. Then we've got depth, which we can increase that depth to start hearing that modulation. You can hear the pitch, that reverb kind of bending up and down. And then the shape, this is exactly like on the MS-20. On the left, we've got a negative sawtooth. On the right, a positive sawtooth. And in the middle, it'd be a triangle wave. Okay, there's some buttons on here as well. There's the diffuse input button, which I mentioned already. There's down here, there's a hold button, which will literally make the reverb last forever. This little toggle button next to the hold will make the hold button either an on-off switch or like a momentary switch. A momentary switch is one that you have to hold down, like the momentary switch on the MS-20. So if we hit this toggle switch, now I can hit that hold and move my mouse away, and the hold will just last forever. If I hit that toggle switch again, now the hold is a momentary switch where I have to actually hold the button down in order to get that reverb to last forever. Over here, there's a clear button. So if we, for instance, have a big bunch of reverb that's adding up and adding up and adding up and adding up, like if we have the hold button down, the clear button literally just clears out that reverb. It's like a reset. So this is good for gated reverbs and things like that, but it's also good just to clear out if you've got like your reverb is blowing up or something. And the last button up here is a tuned mode, and this shortens the delay time and tunes the filters and allows you to actually like produce pitches and stuff with the filter. I'll let you guys explore that on your own. In addition, I'll add a Omri Cohen tutorial video and a link to the website of Plateau, which includes some other tutorial videos. There's a whole lot you can do with this module. It's really involved, and there's some really cool things that you can see people doing in these videos. So I'll post that for you guys to explore that on your own. But let's go ahead and reset some of these and get our patch sounding good before we wrap up. I'm going to turn my dry down and have only wet coming through, since I'm going to use the mixer up here to balance my original, my delay, and my reverb. Speeding up my LFO, which is triggering my envelope generator and my random voltage generator. Let's go to a major scale on our quantizer here. Get something a little more cheerful. All right, that's sounding great. So let's wrap up. So today we talked about sample and hold. We looked at the VCV random module in VCV Rack. We talked about a couple other modules that produce random voltages or do sample and hold, the Audible Instruments Utilities module and the Bog Audio Walk 2. Then we talked about waveshaping. We talked about what waveshaping is and looked at a few examples like clipping and wave folding. And then we looked at two specific waveshaping modules, the Bog Audio Clipper and Volt's Debriatus. And then we ended by talking about delay and reverb. We looked at the VCV Rack delay module and then looked at two reverb units, the Bufaco Spring Reverb and a plate reverb Valley's Plateau. So by now, everything that we did on the MS-20, you should be able to do in VCV Rack. And so I encourage you to look through your notes, think through the things that we did, maybe look at a picture of the MS-20 online, and think about everything we did on the MS-20, whether it's using envelopes to shape the filters, creating inverted envelopes, reverse envelopes, doing frequency modulation, doing sample and hold with pink noise or sawtooth waves or things like that. Think about the things that we did on the MS-20 and make sure that you know how to do them in VCV Rack, because from here on out, starting next week, we're going to be looking at all new stuff, things that we haven't done before, like working with sequencers and things like that. If there's something that you can't do, by all means, let me know, and I'll be happy to walk you through that. I'll be posting a quiz at the end of this week. The quiz will be available on Friday. It'll cover the things that we've talked about since the midterm. And I'll send out an email with a little more info about how that quiz is going to work, when it's going to be up, how long it'll be up, and all those details. So look for that from me soon. Otherwise, have a good rest of the week, and I'll post another lesson shortly.